Hello everyone, I'm Shubhayan Sahu. I'm a PhD student at the University of Maryland, and today I'm going to show you an experiment which will demonstrate Hooke's law and simple harmonic motion. So let me go over the apparatus a little bit. So what we have here is a hanging spring that you can see here, and I have 4 masses with me, each of 200 grams. And what I'm going to do is I'm going to hang these masses from the spring, and we'll demonstrate simple harmonic motion. So a few things to make note of. We have a ruler here which tracks the displacement of the spring, and we will have a stopwatch which will track the time period of its motion. So I'm going to hang, say, 200 grams first, then I'm going to increase it to 400 grams and 600 and all the way up to 800 grams. At each point, I'm going to make 2 computations. One is when I hang these masses from the spring, I'm going to track the displacement of the spring because of the mass at rest. So for example, I hang this mass here. So as you can see that the spring is elongated. I'm going to hold it still, and then I'm going to track what is the displacement of the spring because of the mass. And I'm going to keep doing this for the 4 different masses. Now what I'm going to do is I'm going to disturb it a little bit. I'm going to extend the spring a little bit and then track the motion of the mass as it bobs up and down. So what I want you to think about before I start doing the experiment properly is make a prediction in your head. What is going to happen when I increase the masses? So do you think that as we increase the masses, the time period of the motion will increase, or will it become shorter, or will it remain the same? Right, so let me get started. So this is a multi-step experiment. So what I'm going to do again is I have just the spring here, and we are tracking the height of the spring without any masses on. So now let me hang a 200 gram mass from this, and let me try to hold it still. So as you can see that the spring has been extended, and from this data what you can already find out is the spring constant of the spring. So remember that we have this equation which is k into x equals to m into g, where k is the spring constant, x is the displacement, m is the mass of this bob, and g is the acceleration due to gravity. So just by this, from the data that we found out here, we can estimate what is the spring constant of the spring, right? So make a note of that. So next thing that I'm going to do is I'm going to disturb this spring, and we are going to track the time period of its motion, of the motion of this mass as it bobs up and down. So let me pull it down to 70 centimeters, the length, and then I'm going to leave it. So now I'm going to repeat the same experiment for the 4 different masses. So let's go ahead. And again, we track the length of the spring, and we track the time period. Right. So now that we have seen the experiment, let's try to dig into the data and see what we can get out of that. So what we have here is a series of the masses, so 200, 400, 600, 800, and then we have the displacement of the spring due to that. So when you plot that into a graph, as you will see, it follows a straight line, and the slope of this line will give you the spring constant. So now let's come to the second computation. The second computation that we tried to do was estimate the time period. So as you can see from the data, the time period for the 800 gram mass is twice the time period of the 200 gram mass. And note, 800 is 4 times the mass of 200. So what we see here, that the time period is proportional to the square root of the mass, and because 800 grams is 4 times the 200 gram mass, the time period of the 800 gram spring mass system is 2 times, which is square root of 4 times that of the time period of the 200 gram mass. So this whole experiment demonstrates Hooke's law, and also the basic features of simple harmonic motion very clearly. Thank you.